Hi, my name is Hannah Klion. I'm a postdoc in the Center for Computational Science and Engineering within the Applied Math and Computational Research Division. And today I'm going to be talking about the work I've been doing since I joined the lab on particle and cell simulations of relativistic magnetic reconnection. So to give some context about why magnetic reconnection is an interesting problem, I want to talk about pulsars. Pulsars are some of the most extreme environments in the universe. They're a type of neutron star, which is an incredibly dense remnant of a supernova. Neutron stars have masses of about 1 to 2 times that of the Sun, but are much, much smaller, down to a radius of 10 kilometers. So imagine taking the Sun, with its radius of 700,000 kilometers, and then shrinking it down so that its diameter is twice the width of San Francisco. Pulsars are rotating, with periods of 1 second down to a millisecond. And they also have very strong magnetic fields reaching 10 to the 8 Tesla. For comparison, the strongest continuous magnetic field produced on Earth is less than 50 Tesla. Pulsars also emit beams of radio waves and other types of light along their magnetic axis, and that's probably what they're best known for being these cosmic lighthouses. Because as the pulsar rotates, the beam can cross into our line of sight, producing a radio pulse. But how is this light emitted? We have some sense that it has to do with radiation from charged particles accelerating in the magnetic fields, but we don't have a rigorous first principles model for it. And to further complicate or enrich the picture, pulsars are also home to some of the most energetic particles in nature. Gamma ray emission from nearby pulsars implies the existence of electrons with energies in excess of 100 mega-electron volts, which are not expected from idealized astrophysical particle acceleration theory. So this suggests that there are some non-idealized physical effects at play. So this leads to the question of, can we perform a first principle simulation of pulsar particle acceleration and photon emission? One of the non-ideal processes that's expected to accelerate electrons and positrons is magnetic reconnection. The main thing to know about magnetic reconnection is that it's a particle accelerator, converting magnetic field energy into plasma kinetic energy, both heating the plasma and also accelerating the bulk fluid. In all of the systems I'll be talking about today, we have adjacent regions of plasma with anti-parallel magnetic fields. In this diagram, that's these regions with red and blue field lines. And between these regions, there's a current sheet that's induced by the gradient in magnetic field. The field lines are attracted to one another, causing the plasma to flow towards the center, in this case down. The lines break up and reconnect and then flow outwards, in this case horizontally, heating and accelerating the plasma. As this happens, the current sheet won't stay in this nice little line. It'll fragment into what are called flux ropes due to the plasmoid instability. So these structures are characteristic of magnetic reconnection and are something that we'll see in our simulations later. In addition to being the likely source of particle acceleration near pulsars, reconnection is also a cause of solar flares, the aurora borealis, and in less astrophysical terms, can be a problem in fusion reactors. So on the left, this is a cartoon diagram of a pulsar. There's the neutron star at the center, and then we have charge density indicated by the blue and red contours. So along the equator, there's a current sheet, and surrounding it, there are anti-parallel magnetic field lines. So we expect this to be one of the primary sites of reconnection in the pulsar setup. To self-consistently simulate both of these, both the pulsar and the current sheet in the same simulation, we need to be sure that we're capturing the non-thermal kinetic particle distributions, which require resolving down to at least 1 centimeter, while also tracking bulk outflows of material, which would require a domain several times larger than the 10-kilometer neutron star. So this is a scale difference of 1 million, and so doing it in 3D on a uniform grid would be completely infeasible. The state of the art for these simulations is a domain of about 10 to the 3 to 10 to the 4 cubed, and these have all been on a single grid, and to our knowledge, there have not been any 3D pulsar or magnetic reconnection simulations with mesh refinement. And even if we were able to use mesh refinement on the current sheet, it would still be too computationally expensive since we'd still have to bridge another factor of 1,000 to 10,000 in resolution. So there are two alternative ways that we can proceed. One approach is to scale down the pulsar simulations, so this ratio of length scales is smaller. But then the question is, how does this scaling affect the results? Because the plasma scales are completely different than in the physical pulsar problem. Another approach that we can take is to do detailed simulations of reconnection only, with the motivation of, well, one, of course, learning about reconnection, but also seeing if we can develop physically informed subgrid models of reconnection that we can then include in the pulsar simulations. Both of these approaches require understanding the particle kinetics, so our tool of choice is particle and cell methods. In the particle and cell method, the plasma is represented by macro particles on a spatial grid. Each of these macro particles represent an ensemble of electrons or positrons in our case, or electrons and ions. A time step in a PIC simulation involves calculating the forces on the particles, moving the particles accordingly. As the particles move, they deposit charge and current onto the spatial grid, which are then used as the source terms in Maxwell's equations, which are solved to calculate the electric and magnetic fields, which are then communicated to the particles. The particles we compute the forces on the particles, and then move the particles accordingly. So that's one time step, and then this continues until we've reached the desired final time. To do these PIC simulations, we need a very large 2D or 3D computational domain, as I previously mentioned. So we need exascale resources. And WarpX is an open source particle and cell code built on AMReX, funded by the Exascale Computing Project that has advanced algorithms designed for plasma accelerators. Since it's built on AMReX, which handles domain decomposition and provides a framework for performance portable application design. One advantage of WarpX is that it has mesh refinement, which is very challenging to do in PIC. So it's an excellent starting point if we wanted to perform the first reconnection and pulsar simulations with mesh refinement. WarpX currently implements a single level of static mesh refinement. So once we have if we were able to get a single level working, we would hope also to be able to expand to multiple levels and or adopt an adaptive scheme. In addition, the other things we're doing for the pulsar problem are there's additional physics we'd like to add, and then in terms of things we've already added, there are some additional diagnostics to do with cell averaged particle quantities to get a bird's eye view of what the particles are doing, as well as relativistic momentum initialization for setting up our reconnection problem. One of the advanced algorithms implemented by WarpX is a pseudo-spectral Maxwell solver. So Maxwell's equations are partial differential equations in both space and time. And the most popular way these equations are integrated in PIC is the Finite Difference Time Domain method, or FDTD, where spatial derivatives are calculated using a second order finite difference stencil, and then the equations are integrated numerically, again, second order scheme. Another approach is the pseudo-spectral analytical time domain method, or PSATD, where the spatial derivatives are computed in Fourier space, and it also happens that in this formulation, the equations can be integrated analytically in time. The scheme is more accurate than FDTD and allows for longer time steps due to the analytic time integration. However, it's never before been applied to relativistic reconnection, and we want to see if we can use it to make our simulations more efficient, which will be particularly impactful as we move to 3D. So our astroplasma group is working on both of these approaches, but for the rest of this talk, I'm going to be focusing on my work on prong number 2 here, the detailed simulations of reconnection. So the first step in all of this is to establish a really good baseline case. So we can compare both to the theory where possible and also to the literature, because there's no analytic solution to compare to here. This will give us a place to develop diagnostics for the plasma and also to benchmark computational accuracy and performance. So we start with a pair of current sheets in 2D in equilibrium. So we have our anti-parallel magnetic fields. There's two flips in the direction of the magnetic field, and between those flips we have current sheets, which the top one's going into the page, the bottom one's coming out of the page. And we have this double current sheet set up so we can apply a periodic boundary condition both horizontally and vertically. These current sheets are hot, and the gas pressure is what's keeping the plasma in equilibrium and resisting the attraction of the magnetic field lines to one another. The plasma here has the same scale as the physical pulsar problem, which is a relevant length scale of about 1 centimeter, and the current sheets are somewhat larger than that with a thickness of 5 centimeters. The box is about 10 meters by 20 meters, and it's worth noting that this is about the size of a single cell in the largest pulsar simulations. The main physics we hope to extract are the particle energy distribution, given that we're interested in particle acceleration, but we're also interested in what's called the rate of reconnection, which is the rate at which the magnetic field lines are breaking up and reconnecting. And much of the theory around reconnection is written in terms of this reconnection rate. So it's a good thing to have in order to compare with the literature, and also as a way of validating the physics we're seeing. So if we were to leave this setup to its own devices, it would eventually reconnect. There's enough noise in the local particle distribution that the magnetic field lines will eventually overcome the current sheet in a few random places due to drops in pressure, and reconnection will begin. But one, that can take a long time and we don't want to waste computing resources, and two, it won't allow for an apples to apples comparison between the solvers. Following some examples from the literature, we apply a 1% perturbation to the magnetic field, which pinches in the magnetic field lines at the center of the domain. And this will induce a reconnection to start in the same way, at around the same time, regardless of the numerical solver we're using. So I'm about to show some movies from our simulations of relativistic reconnection with FDTD on the left, and the first simulations with the pseudo-spectral Maxwell solver, PSATD, on the right. So we start off with our current sheets in orange and purple, and then the anti-parallel magnetic field lines. And as this starts, pretty much immediately the current sheet fragments into these plasmoids that I showed earlier, at around the same spot, at around the same time. And eventually we're left with a single large plasmoid as the overall reconnection has saturated. These simulations take about an hour to run on about 120 GPUs on Summit. So currently they're very tractable, but this is just 2D. And in 3D, it's going to be substantially more expensive. But one thing that's been really challenging here, and it has been working on getting the load balancing efficiency to be good. This was something that Michael Rowan did a lot of work on when he was a postdoc here, on making sure that as the plasma flows into the current sheet, and so as the density of macroparticles increases there, the AMReX computational boxes are distributed appropriately among the GPUs so that we don't have 1 or 2 GPUs doing all of the work and slowing down our simulation. Qualitatively, we get similar results from the different solvers. This is fairly early on. This is a still from fairly early on in the simulation, and the locations of the plasmoids are relatively similar between the two solvers, and we have our single large plasmoid on the forming at the grid boundary. So the first thing we'd like to verify is that we aren't violating any basic conservation laws. So the bottom left panel shows total energy on the domain as a function of time. The dashed lines show the energy and the electromagnetic fields, and the solid lines show the particle energy. The different colors are for the different solvers, with the finite difference in blue and the pseudo-spectral in orange. As the simulation progresses, electromagnetic energy is converted to the particle energy, and once about 40% of the electromagnetic energy has been transferred to the particles, reconnection saturates and the system stabilizes. On the right, we have the relative change in total, so that's electromagnetic plus particle, energy as a function of time. With both solvers, we're seeing energy conservation to within 1 part per thousand. The pseudo-spectral method does slightly better than the finite difference method, but both solvers are well within the tolerance that we'd hope for, so we're very happy about this. The reason we wanted to try PSATD in the first place was to see if we could improve computational efficiency, and the answer appears to be yes. The wall time per time step in the finite difference and pseudo-spectral simulations are comparable to one another, about 0.3 seconds per time step. But as I mentioned earlier, we're able to take longer time steps with PSATD. Consequently, the PSATD simulation is about 30% faster than the finite difference one, and we're hopeful that we'll be able to push PSATD to longer time steps, or also possibly use a larger cell size than an FDTD, which will be particularly impactful on efficiency as we move to 3D simulations. So one of our stated physics goals for these 2D reconnection simulations was to extract the particle energy distributions, and we've been able to do that. So here we've got the initial histogram of particle velocities, so essentially a proxy for energy, focusing just on the center of one of those current sheets. As time progresses in the simulation, the high velocity tail sweeps outwards, indicating that the particles are being accelerated just as we expected. There's also an overall increase in the normalization of the distribution, since plasma flows into the current sheet and then gets trapped. It's also nice to see that these solvers are producing similar distributions throughout the simulations. The power law slope of this particle energy distribution is an important diagnostic that's frequently calculated and quoted in the literature. So this is a similar plot to the ones in the last slide, but shows particles across the whole domain. The initial distribution is in blue and the final is in orange. And we can see, as before, that the abundance at higher velocities or higher energies increases from the start to the end of the simulation. These quoted power law slopes from the literature are plotted in these black solid and dotted lines, and we see relatively good agreement with our final distributions. So we're quite happy with our preliminary agreement with the literature with these results. So what's next? One of the other physics goals I mentioned way back at the start was to try to extract the rate of magnetic reconnection. So that's something we're working on now. And we're also working or thinking about adding mesh refinement, which has never before been applied to relativistic reconnection simulations. We can't just turn on mesh refinement and expect it to work out of the box though, because the pulsar plasma is in a different region of parameter space than the accelerator plasmas that WarpX's mesh refinement was designed for. So we may have issues with accuracy or performance. But our collaborators on the WarpX team include experts on mesh refinement and PIC, so we'll be well positioned to make progress on this front. And there's also additional physics we'd like to add to more accurately simulate the particle energy distributions. We'd also like to extend to 3D, and that's something that we're currently working on. We have some promising pilot 3D runs. We expect additional plasma instabilities to emerge, like this bending in these flux ropes. And we also expect for there to be changes to particle energies and reconnection rates. And a very lofty goal is thinking about how we could possibly combine PIC with magnetohydrodynamics methods. And of course, we're continuously thinking about what can we learn from these detailed reconnection simulations to improve our pulsar models. I'd like to thank the WarpX team for their help in making this work possible, also the Astroplasma group, especially Reva Jambunathan and Michael Rowan, who have been my primary collaborators on this project. To summarize, I've been doing simulations of magnetic reconnection using particle and cell methods, and we're looking towards 3D simulations and mesh refinement in order to bridge this factor of a million scale difference between the pulsar and plasma kinetic scales. We are working on scaling down this difference, but we're also thinking about working on zooming in to the reconnection itself in order to further refine the pulsar simulations. Thank you.